In the last lecture, I was using data on the demand for consumer durables in Canada to illustrate how we can use one of the two-stage sequential testing procedures to determine dynamic specification. And at the end of that exercise of applying the procedure 2 in its forms both A and B for the models relating consumption to income and the price of durables relative to non-durables in both levels and logs, the provisional conclusion was that the order of dynamics is 4, and that fourth order dynamics in the model is unlikely to be represented by a fourth order autoregressive error process. Also, from inspection of the results for the logs and the levels model, it appeared that the logs model was slightly preferable to the levels. And that comes about largely on the grounds that the goodness of fit is much the same, and the chi-squared test for parameter stability outside the sample period was much better for the logs model than the levels model. So where do we proceed from there? Well, the first point and the most important point is that when we're looking for model selection procedures, and in this case model selection in dynamic models, we should never really hope to have a purely mechanistic procedure for selecting models. And procedure 2, A and B, is a purely mechanistic procedure for selecting the orders of dynamics and then discriminating between systematic and error dynamics. In fact, that analysis is almost pure data analysis. And the only economic theory that went into that exercise was the selection of variables at the beginning. Namely, we were choosing consumption expenditure on durable goods as the variable to be explained, and we related that to an income variable and then to a relative price variable. And this is part of the economic content that we've used. The other economic information that we've used is prior beliefs about the size of elasticities of consumption with respect to income and with respect to price. So that for that analysis, that really was the only economic analysis that we've introduced, the selection of variables, and then we compute the elasticities and see whether they're sensible or not. But more generally, we should never aim to select models by purely mechanical procedures. And the major reason why we shouldn't do that is that a purely mechanical procedure can often miss the really important aspect of some model. So if there is a particular nuance for the data generation process for a particular variable, if you use a purely mechanistic procedure for selecting your model, then it's quite likely that you will miss that particular aspect. So should we reject this data analytic approach to model selection? Well, I would argue that we shouldn't reject that, and what we should now do is use that to indicate the order of dynamics that we're likely to need in an economic theory-based model, and also as an indication as to whether that dynamics can be represented by autoregressive error processes or by systematic dynamics in the model. And finally, we should use models that have been used by generating models using this purely mechanistic approach. We should use those to be benchmarks against which we can compare economic theory-based models. And by that I mean that if now we generate a new class of models from economic theory, then those models have got to do at least as well in terms of goodness of fit as the purely data analytic models. And if they don't, then the economic theory we're using hasn't performed well for this particular data set, and therefore we ought to reject it. Well, returning to the demand for consumer durables in Canada, we now believe that the order of dynamics should be something like 4 periods for quarterly data, and that it's probably not generated by an autoregressive error process. But noting that Canadian data has an extremely marked seasonal pattern, and probably more marked seasonal pattern than any other country's data, then it is not a surprise that we've got 4th order dynamics coming up in the model. So that, remembering that highly seasonal characteristic of Canadian data, if we now consider models of the following type, when we're going to use log formulations because the previous analysis indicated a slight preference for log models rather than levels. And delta 4 is, in this case, a seasonal difference, 1 minus the lag operator to the power 4, equals beta delta 4 log yt minus delta log ct minus 4 divided by yt minus 4 plus sigma I is 1 to 4 si, capital Si t plus ut, where, to remind you, C is the expenditure on consumer durables per capita and deflated by the price index for durable goods. YT is a GDP, gross domestic product variable, an income variable, which has been deflated by the price index for expenditure on all consumer goods. So, if we like, we can denote the consumption variable CT by the nominal expenditure per capita and divided by the price deflator for durable goods. And similarly, the income variable is the nominal GDP variable per capita and divided by the price index for total consumer expenditure. This is just durable, that's total. Then capital SIT is the dummy variable which captures seasonal shifts in the intercept. And given that we're using quarterly data, these are seasonal dummy variables, which takes the value 1 in the ith quarter and 0 in other quarters. And the small si's are the coefficients. UT is just a random error. Well, if we now consider models of this type, let's analyze some of their properties. Because a model of this type does have the characteristics that were indicated by the preliminary data analysis to determine dynamic specification, namely 4 period lags, and it doesn't have an autoregressive representation. Well, if in that model delta is not equal to 0, then we have the interesting model that I want to analyze. But also notice that if in fact delta is 0, then this becomes a model in the seasonal differences of the logs of the interesting variables C and Y. And that in fact is a model that we're quite likely to be considering. had we adopted a Box-Jenkins approach to the relationship between C and Y. We may well have used the log transformation to get the variance of the variables stable. So used the log as a variance stabilizing transformation. We then looked at the parallelogram for the log of CT and saw, not surprisingly for Canadian data, that it's got peaks at the quarterly seasonal terms, so that we then take the seasonal difference. And if delta is 0, this term disappears, and we would then, using that methodology, be attempting to model the seasonal difference of the log of C related to the seasonal difference of the log of Y. And so an interesting question is whether delta in this more general model is equal to 0 or not. If it isn't equal to 0, then by using the first step in the Box and Jenkins type approach of looking at the parallelograms for the variables and then differencing until the parallelogram looks as though it's the parallelogram for a stationary variable, is likely to lead us to inappropriate models. So this is an interesting hypothesis as to whether delta is equal to 0 or not. Let me repeat some of the arguments I made previously against taking seasonal differences in this particular context, so that if in fact delta is equal to 0, then the thing we have to notice is that if we have a unique path for the log of yt, then the path of the log of ct is determined by that path of the log for yt, independent of any disequilibrium that's been in the past. So that one reason for using a model of this type, as far as the economic theory is concerned, and that is a model in differences, is that the difference formulation will capture the short-run disequilibrium behavior. That's a different justification for using delta 4 to the Box and Jenkins justification. But if in fact in a model with the delta 4s in, this delta is 0, then the adjustment in the short period is completely independent of the disequilibrium in any previous periods. And that's precisely the reason why this term is introduced, the delta log of the ratio of C to yt. That represents disequilibrium. Also notice that if in fact this term doesn't occur in the model and we estimate the model in the seasonal differences, then that model is incapable of telling us anything about the long-run relationship between C and Y. Because in the long run, the delta operator on any variable becomes 0. Because by the long run, I now mean that CT takes the same value in all time periods. So we're in a long-run equilibrium situation. This delta 4 of log CT will be 0, so also will the delta 4 of log YT. This term is 0 because delta here is 0, and we just have no information at all about the long-run equilibrium solution for consumption in terms of income. And it's information of that type that we get from economic theory. And in particular, in the context of consumption, generally, we have the permanent income hypothesis of Friedman, which can be briefly summarized as proportionality between consumption and income, with a unit elasticity and constant marginal propensity, which is equal to the average propensity to consume. And that comes from the permanent income hypothesis, which we could only expect to hold in the long run, because the Y in this must be permanent income, and that is the long run level of income. So that if we are going to use information from economic theories similar to the one of Friedman, then we do need to have within our model the long-run equilibrium solution. And again, that's precisely what this second term on the right-hand side of the equation is designed to incorporate in the model. Well, let's now consider the situation when delta isn't equal to 0 and assume that there's a constant growth rate in both C and Y, and they're equal, and for the time being we'll replace the error term by its expectation of 0. So we're now assuming that in the long run delta 4 log of C is equal to delta 4 log of Y, and both are equal to a given growth rate, G. And what we're doing here is saying that delta 4 is acting like a differential operator on the log of C, and therefore we're getting a growth rate. Well, if we assume that, namely a constant growth rate for consumption and for income, and substitute into this equation, we have that G would be equal to beta G minus delta the log of C divided by Y plus the seasonal dummy variables. And that gives us a solution in the long run of exactly this form, where if we solve that now by taking solving it for the log of C in terms of all other variables, and then taking the exponential of that expression, we get an expression of that form when K is equal to the exponential of minus 1 minus beta times G minus sigma SI SIT I is 1 to 4 divided by delta. And so a model of this type, which has this delta not equal to 0, in the long run has a solution of this form. And what are its characteristics? Well, the long run elasticity of consumption with respect to income is unity. The long run average propensity to consume is equal to the long run marginal propensity to consume, both of which are equal to K. And what can we say about K? Well, first of all, because we've got these seasonal dummy variables and their coefficients in K, the long-run marginal propensity to consume can vary seasonally. So that if the small si's are significant in the estimated relationship, in the long run, if delta is not equal to 0, then the marginal propensity to consume does vary seasonally. And that may not be an unreasonable description of reality. Also notice that the marginal propensity to consume varies with the growth rate, and in particular it varies inversely with the growth rate. So the higher the growth rate, the lower the marginal propensity to consume, which seems to be consistent with cross-sectional data when the cross-sections are comparisons of consumption relationships for different countries. So that the higher income countries have lower marginal propensities to consume than lower income countries. So that a model of this very simple type, which corresponds to our fourth order dynamics, does have some desirable economic characteristics. Before going on to see how well models of this type performed with the Canadian data, notice what happens in this model if, in fact, delta is 0, as far as the long-run elasticities are concerned. If delta is 0 in this model, then the long-run elasticity of consumption with respect to income is equal to beta. As this term disappears, then again we're just using the ratio of these two expressions as a definition of elasticity. And the ratio is in fact beta. Finally, notice that if we were to include either Ct minus 4 or Yt minus 4 in log form without any restriction in this model, so let's say the log of Ct minus 4, then this model can be rearranged to be a model in the levels of the log of C and the log of Y. In other words, although we've parameterized it in terms of seasonal differences and some levels and ratios, in that extended form, this is formally identical to a model which only involved the log of the levels at t and t minus 4. So that in this formulation, we could directly test whether the delta 4 representation is appropriate. Why then would we use this model, in addition to the fact that it allows us to test for the delta formulation? Well, a very strong reason for using this formulation is that if we did have a regression in the levels of all the variables at t and t minus 4, and if in addition we included the intermediate lags, then it's quite likely that we'll have quite a high degree of multiclinearity between the variables. And so not be able to determine the coefficients very precisely. With this formulation, delta 4 of the log of Yt is more likely to be orthogonal to the log of Yt minus 4 than the variables log Yt minus 4. We could either include those two variables in the regression, which are likely to be collinear. Alternatively, we could have delta 4 log Yt and the log of Yt minus 4, or the log of Yt. And to include these two variables is equivalent to including those two variables in the model. However, these two are likely to be collinear, and therefore will determine the coefficients imprecisely. These two variables are now likely to be much less collinear. The delta 4 is removing the seasonal component from Yt, and this is just representing the level of Yt. So if we have models in delta 4 and the level, we're likely to determine their coefficients more precisely. That doesn't mean to say we've removed the multiclinearity problem, because there is still a mapping from these coefficients directly back to the coefficients of the original formulation, and in terms of the estimates of the coefficients in this original formulation, we will still have imprecise estimates. But what is important is that we can estimate the coefficients of the delta and the level more precisely, and in addition, these coefficients do have some economic meaning. In fact, more meaning than probably the levels in the original formulation might have had. And in particular, if we were now concerned with explanation for the log of consumption at time t, and we had that as a function of those two variables, then this delta 4 of the log of Yt is attempting to represent the effect on consumption of the increase that's occurred in income over the year. And we look at the consumption in a particular quarter and relate it to the change in income by looking at the change in income in the same quarter relative to that corresponding quarter of the previous year. So that this is the seasonal change in income, and we have consumption as a function of that. We then have consumption as a function of the level of income in the same quarter but of the previous year. So this variable represents the overall level of income for the appropriate quarter of the year, and this is now representing the way in which income has changed through the current year. And those two variables are highly likely to determine what happens to consumption in this particular period T. Well, so much for the arguments as to why we might consider models of this type. If you look at the second page of the handout from last week, we have the results obtained when I estimated models with this structure, namely the alternative lag models. And if you look at the first model, that has exactly this structure, but in addition we have delta 1 of delta 4 log yt, so that the delta 4 of log yt is looking at how income has changed through the year. The delta 1 of delta 4 is now the rate at which that income is changing through the year. So if you like, this is an acceleration effect for the changes in income that's been introduced. And in addition, we have delta of the log of the relative price variable. Price of durables relative to non-durables at time t, with a constant term as well. And looking at that, the results for that equation, first of all notice that the constant term was not significant. Which in the context of this long-run solution means that although we haven't allowed for seasonally varying intercepts, this term, or the analogous term to that in this model, which is just the constant term, doesn't appear in K. So we don't have a constant term coming in there. And so that the marginal propensities to consume in the long run only depend on the growth rates and delta, the coefficient of the log of the ratio. But otherwise, the long-run elasticity with respect to income is 0.75, and that comes about because in the estimates, delta is not significant. So the coefficient of the log of the ratio has a t-value of 1.2, and so for that formulation, delta is not significantly different from 0, and therefore the long-run elasticity of consumption with respect to income is equal to beta, and that was 0.75. And for a long-run elasticity of consumption with respect to income, certainly in the light of the Friedman analysis, is quite a small long-run elasticity. Well, the next modification is to allow for the possibility that rather than having a single constant term in the model, we should have a seasonally varying intercept. And if you look at the results for the second equation, we have the seasonal dummy variables included. And for that model, sorry, this is the third set of results for C. For that model, the results indicate that now the intercepts, which vary seasonally, are significant. So that for this model, those terms now do enter the long-run relationship. And in addition, the coefficient on the log of the ratio of C to Y is now significant as well. So that for this model, the long-run elasticity of consumption with respect to income is now unity. As soon as delta becomes significant, this long-run elasticity becomes unity. So that model C has the long-run elasticity of consumption with respect to income equal to unity. It has the long-run average propensity to consume and marginal propensity to consume, which is K, varying seasonally, because we now have significant seasonal dummy variables. And altogether, that looks to be a much better model than the first one. However, if we were to work out the long-run elasticity of consumption with respect to the price variable, then that turns out to be plus unity. In fact, that's the long-run elasticity of consumption with respect to the price ratio, which is the price of durables relative to the price of non-durables, and that turns out to be plus unity. And so we might want to question that model. The second set of results were tackling the problem which is to determine, in fact, whether the elasticity in the long run of consumption with respect to income varies seasonally. And that was done by, in effect, introducing a different delta for each quarter of the year. And if you look at the results under B, you'll find that none of the deltas, which now are different deltas for each quarter, is significantly different from 0. So the purpose of the results B is to test the hypothesis that the long-run elasticity of consumption with respect to income might vary seasonally. And the answer is that it doesn't. So if we go back to the result C, and because we may be a little unhappy with this result, inspect the correlogram of the residuals, what you find is that it has a bump at lag 4. So that although we have a model which has 4-period lags in all the variables, this particular model still has a bump at lag 4 in the residual correlogram. And so there's still part of the dynamics that hasn't been captured by this model. Well, at this stage, if you go back and look at the results for the log model with m equals 4, that is from applying the procedure to either A or B, and then look at the model for the logs with m equals 4, then you'll find that the price variables, which were included currently and with 1, 2, 3, and 4 lags, were in fact significant at lags 1, 2, 3, and almost significant at lag 4. And in particular, that the coefficients suggest that they satisfy this relationship where the small p's now are indicating the logs of the original relative price variable. So that you can rearrange all the coefficients in that unrestricted model to be in that form. And the interesting thing is that we have the level of the price at t minus 4 occurring in the model. So that if we now introduce terms of this type into the disequilibrium model, we get the results under D. And what you find there is that the coefficients on both of these terms are highly significant, and the coefficient on pt minus 4 as a level has a t ratio of 1.3, so that it's not, by conventional criteria, significant. But if you inspect the residual parallelogram for this model, you now find that it doesn't have the same bump at like 4. So the indications are that by including the price variable at t minus 4, and that comes in this difference and the level, that's removed the problem of the bump in the parallelogram at 4. And in fact, Model D does perform quite well in explaining consumption. Because if we look at the other statistics for those results, we have quite a high value of R squared, remembering that this is the R squared for a dependent variable, which is delta 4 of the log of CT. And the R squared is 0.7, which is a high value for a dependent variable of this type. In addition, we have the chi-squared statistic with 6 degrees of freedom, which is now using the 6 observations that we didn't use in the estimation of the model. We retain them for parameter stability tests. It's testing whether the parameters are stable in this forecast period, and that test statistic had a value of 3.56, which is clearly less than the critical values of a chi-squared with 6 degrees of freedom, again, at most significance levels you would want to use. The other reasons why the model now is acceptable on economic grounds are that in the long run the income elasticity is, because delta is estimated to be significantly different from zero unity, the elasticity of consumption with respect to the price of durables is minus unity. And that comes about in the following way. If we again assume that we have steady growth in consumption and income at the same rate G, and then use the results that we've got for the estimates D, we have that G is equal to the seasonal coefficients plus 1.06 G minus 0.34 log C divided by Y minus 0.36 the log of the price term. And remember that the price is the price of durables relative to the price of non-durables. And if we solve that now for the log of C, we have that the log of C is equal to the seasonal terms plus 0.06 G minus 0.36 the log price of durables relative to the price of non-durables, all divided by 0.34, and plus the log of y, which gives us our solution for the long-run equilibrium. Consumption is the exponential of the seasonal terms plus 0.06 g on 0.34 into the income variable, and PD upon Pn to the minus 1. And that minus 1 is coming because I'm assuming that that 0.36 is not significantly different from the 0.34. So that when we take those two terms together, that becomes minus 1 as the coefficient or the exponent of PD divided by Pn. But then remembering that C was C star upon the price of durables, and in fact also divided by the population, and that Y was Y star divided by population and PT, we have that C star upon N, per capita nominal expenditure on durables, is equal to this constant K, which is the exponential of the curly bracketed expression, into Y star PD of PT into Pn upon PD. And certainly the price indices for the durables would cancel, and we can say that approximately we have that nominal consumer expenditure on durable goods per capita is proportional to the nominal GDP per capita. So that the nominal expenditure on durable goods is zero homogeneous in prices. Again, a feature which is often thought to be a reasonable description for an economic model. So that from this analysis, the results we have for the equation D do appear to be reasonable on economic theory grounds. And in fact, the results D are the ones which I would say as being the best for the explanation of the expenditure on consumer durables in Canada at the present time. This equation does in fact forecast very well. It does have these desirable characteristics as far as economic theory is concerned, and if you look at the structure of the model, it is similar to the structure that we got from the purely mechanistic time series analysis. But it does have much more economic theory involved. Well, that is the end of the illustration of the use of the sequential testing procedure for determining dynamic specification. And in fact, all I've done so far is to analyze that procedure theoretically and say that asymptotically we can say that such a procedure will have high relative asymptotic efficiency. And we can't say much more than that. So that an interesting point is how well do these procedures perform in small samples. We've seen that in the illustration for the Canadian consumer durables demand, that the time series modelling did point to a model very similar to the one which economic theory is consistent with in the end, but that isn't a strong recommendation for the procedure. So that what we could now do is undertake a Monte Carlo study of the size and power characteristics of the test for dynamic specification. And in particular, a Monte Carlo study of the size and power of the walled test for dynamic specification. Well, in doing this, we must first of all distinguish our econometric model from the Monte Carlo model. And the econometric model, whatever it is, will be embedded within the Monte Carlo model. And the Monte Carlo model has as its objective to determine estimates of the size and power of the walled test statistic, so or the W statistic. And the important point is that all we can do is get estimates of the size and power of the test statistic in small samples. And because they're estimates, we're going to have sampling variation, namely the simulation variation. And if possible, we want to be able to reduce that simulation variance. We want our estimates to be as accurate as possible of size and power. We want to reduce the simulation variance. So if there are any methods available for reducing the simulation variance, we should use them. Secondly, we should notice that the population parameters of the econometric model become the design variables for the Monte Carlo model. And so if we want our results to be representative of situations which occur in practice for econometricians, we must be very careful in choosing the values of these design variables to represent the appropriate ranges. Finally, when we do have the results for a particular design for the experiment, the estimates of size and power, it could be said that those results are particular to the design of this experiment and won't generalize outside the range that we've chosen for these population parameters in our design. And what we should do as a final stage of the Monte Carlo is to consider response functions which relate the empirically determined estimates of size and power in this context to the values of the design variables. And the response functions enable us to reduce the specificity of the Monte Carlo results. And another way of looking at that point is to say that from analytical statistical analysis, which usually is asymptotic, we can derive formula which will relate these characteristics that we're interested in, namely size and power in this case, to the population parameters. So from analytic analysis, we can have analytical formula relating, in this case, size and power to the population parameters. But in this particular context, these analytical formula are only valid asymptotically. And that was our original problem, that these relationships can only be derived asymptotically, and we want to know what happens in small samples. Well, what the response functions are doing are replacing the analytical formula by empirically determined formula. So we now have empirically determined formula relating the power to design variables. So relating size and power to design variables. And if these empirically determined formula have good fit, so for example a high R squared, if we do it via regression analysis, then we have a reasonable formula for predicting what size and power is going to be for a given combination of the design variables, which, remember, are in fact the population parameters. So that despite the fact that the Monte Carlo study can only be done for a small selected number of values for the design variables, if this response function, which is determined empirically, fits very well, we can use that relationship to predict what the size and power will be for values of the population parameters or design variables different from the ones we used in the Monte Carlo. And that helps to reduce the specificity of the Monte Carlo study. So there are a number of stages involved in the design of the Monte Carlo. The first one is to decide what it is you're looking at, and in this case it's the size and power of the test statistic, and we want to estimate those. We then have to specify the structure of the econometric model, which tells us the population parameters. And at that point, we have to look for an efficient design for the alternative values that we're going to consider for the population parameters. We then go ahead and perform the Monte Carlo simulation, get estimates of the size and power. We then want to relate those estimates of size and power to these design variables. Well, first of all, let's consider an essentially static case. So this now is the data generation process, or the econometric model, which we're going to analyze. And we have yt is xt plus an error term ut. And without loss of generality, we've assumed the coefficient of xt is unity. It really doesn't make any difference what value that assumes. So that's the static model. But we assume that the errors are generated by first-order autoregressive error process when the epsilons are normally independently distributed, zero mean, constant variance sigma epsilon squared. So all we now have to do is to specify how the independent variables xt are generated. And a process for generating the x's, which is quite realistic for economic applications, is an autoregressive process. So that we assume that the x's are now generated by a first order autoregression when also the errors vt, normal, zero mean, and now a variance of unity. And again, by restricting the variance of vt to be unity, we don't lose any generality. Because in the design of the experiment, it's the ratio of the variance of vt to epsilon t that occurs. And that, which is important. So we can arbitrarily fix one of the variances and leave the other as a design variable. So this is the data generation process. We're going to have lambda and rho such that the model is stationary. But the model we're going to estimate is going to be yt is equal to alpha 1 yt minus 1 plus alpha 2 xt plus alpha 3 xt minus 1 plus epsilon t. By allowing in the first equation for this autoregressive error process. So we include the lag on y and x in that model. The implication of that is that alpha 1 is in fact rho. Alpha 2 we again assume is unity. It's this coefficient here without loss of generality. Alpha 3 would be equal to minus rho if the true data generation process was the first equation and the second. In other words, there was exactly an autoregressive error representation. But since we want to test the power of the test statistic for this common factor of a first order autoregression, we now want to introduce some non-centrality into the process generating the data. And that we now introduce by letting alpha 3 in the equation we estimate be the minus rho, which it would be if that had generated the data, but plus gamma upon root t. That implies gamma squared is t into alpha 1, alpha 2 plus alpha 3 squared. And the autoregressive restriction that we're wanting to test, or the test for a common factor, is precisely the hypothesis H0 that alpha 1, alpha 2 plus alpha 3 is equal to 0. I'm going to test that against the alternative that it isn't equal to 0. And that is the same as gamma upon root t being equal to 0. So that the Wald test statistic can be written as gamma squared divided by the variance of gamma squared and asymptotically that will be distributed as a chi-squared with 1 degree of freedom on H0, and asymptotically distributed as a chi-squared with 1 degree of freedom and T mu, non-centrality parameter, on H1. When T mu is equal to sigma squared into 1 minus rho squared sigma epsilon squared into 1 minus lambda squared. And notice, we'll later reference that that is gamma squared into the signal noise ratio, whereby the signal I mean the variance of the X process, and the noise is the variance of the error process UT. And that's just sigma epsilon squared upon 1 minus rho squared. So that's where we get the 1 minus rho squared upon sigma epsilon squared. The variance of the error of the process generating xt comes 1 upon 1 minus lambda squared. So this is the structure of the econometric model. This is the test statistic, which is the statistic corresponding to testing that hypothesis, which is the usual hypothesis for the autoregressive restriction. Notice that the alternatives that we're considering are a sequence of alternatives, the gamma being different from 0 upon root t. And the fact that they're divided by root t is to ensure that we're only looking at the power in the neighborhood of the null. Because we know that asymptotically the test statistic is a consistent test, so that away from the null it's got unit power. And what we want to do empirically is to look at the power of the test statistic in the neighborhood of the null hypothesis H0. But how do we define the neighborhood? Well, the size of the neighborhood depends on how quickly the parameter estimates converge to a limiting distribution. And the estimates of the parameters in models of this type converge to a limiting distribution with root t. And that's why we get the division by root t. In fact, these are the form of the alternative hypotheses which Durbin considered in his 1970 Econometrica paper. Well, what are the design variables for this model? Well, the variables that we can control are t, the size of the sample, the serial correlation coefficient for the error process, rho, the autoregressive parameter for the process generating the x's, lambda, and sigma epsilon squared. There is in fact also gamma, but we treat that separately. Well, for rho, we use values of 0, 0.4, and 0.8. Lambda, 3 values of 0.3, 0.6, and 0.9. 0 comes in for rho so that we can evaluate the size of the test statistic when we have rho equal to 0. Sigma epsilon squared equal to 0.1, 1.0, and 10. And the sample size 25, 55, and 75. Now we come to the usual problem. If we were to consider all possible combinations of these values for the design variables, and in addition consider variations in gamma, then we get far too many experiments. So at this stage what we do is to use the Greco-Latin square design for these 4 variables. And in particular, we took plan 4.2 on page 146 of Cochrane and Cox book on experimental designs. So that determined the experiments, 9 experiments in all, for combinations of those design variables. We then performed those experiments for gamma equals 0, gamma equals 1, and gamma equals 2, giving us 27 experiments altogether. Well, as a result of performing those experiments, 27 experiments, and the number of replications of each experiment, which is denoted by n, was 100 in each case, we could then get the empirical size and power. And by that, the empirical power is the number of rejections of the null hypothesis when the null hypothesis is false. So we look at the proportion of the 100 replications which resulted in rejection of the null hypothesis when in fact the null was false. And that gives us an estimate of the power of the test statistic. And we have p hat i's, I going from 1, 2, through to 27 for the 27 experiments. Given the Greco-Latin design on these variables, that gives us 9 experiments, each of those repeated for gamma equals 0, 1, and 2, giving us 27 altogether. What we could then do is simply look at these numbers, rejection proportions, and relate those to the values of the design variables. However, there's one other thing that we can do in attempting to decide what form of response function we should look at, and that is to use asymptotic theory to predict what relationship we would expect between power and these design variables. And in this particular context, what we did was to evaluate p star I, which is the asymptotic approximation to the power. And that was arrived at in the following way. Notice that the test statistic W is asymptotically distributed as a chi-squared with 1 degree of freedom and non-centrality parameter T times mu on the alternative. So that we could evaluate this power on the alternative if we're prepared to use non-central chi-squared distributions. Because we know what the value of this non-centrality parameter is, given our design, and so we can evaluate these powers. But rather than use non-central chi-squareds, which I think econometricians are not too familiar with, we can use a result which is in Kendall and Stewart, which relates a non-central chi-squared to a central chi-squared via a factor of proportionality. And the property is that the first two moments of the approximating central chi-squared are exactly the same as the first two moments of the non-central chi-squared. If we use that as an approximation, we can then evaluate these powers using central chi-squared statistics or distribution. And the approximation is that if we have a chi-squared with n degrees of freedom and a non-centrality parameter phi, we can approximate that by h times a central chi-squared distribution with m degrees of freedom, when m is equal to n plus phi divided by h, and h is equal to n plus 2 phi upon n plus phi. And that's in Kendall and Stewart, chapter 24. Occasionally you'll run into problems that this value for m is not going to be integrable, or it's not going to be an integer, and therefore you need to use an approximation, so interpolation. But by using this, we can now evaluate the power of the test statistic using the central chi-squared distribution the integral from c upon h through to infinity of the differential of the chi-squared with m and non-centrality parameter of 0. And we use this relationship to generate the approximate power of the test statistic w. And that where does C come from? Well, C is defined by the probability of W when gamma is 0 and C is then the lower limit of integration d the chi-squared with 1 and 0 degrees of freedom. With those two relationships, we can now generate the P stars, which are the asymptotic approximations to the power. If you analyze these expressions for the power in a little more detail, you're able to show that the Wald test statistic is a consistent test. And even when you use the approximating central chi-squared, you still get the approximating power function corresponding to a consistent test statistic. Well, in the remaining time, let me now look at the results which are obtained for that particular Monte Carlo experiment. And the first four columns represent the values of the 4 design variables for each of the 9 experiments. And those 9 experiments were repeated 3 times for each value of gamma. Gamma equals 0, 1, and 2. P hat is the empirical rejection frequency. P star is that asymptotic approximation using the central chi-squared. And what do we notice? Well, for gamma equals 0, that means that there really is an autoregressive error process generating the first-order dynamics in the model. And therefore, the probability of type 1 error here is the size. So the probability of rejecting the null hypothesis of first-order autoregression, when in fact there is first-order autoregression, is exactly the size of the test. And we're setting that at 5%. So that the asymptotic powers, which in this case are sizes, are 0.05. The empirical values in this case, when there is an autoregressive error process, vary from 0.1 through to 0.04. But an important point to re-emphasize is that these empirical powers, or estimates of the size, are estimates and have a sampling distribution. And in fact, because we've taken those to be the proportion of rejections in the sample, or within the number of replications, the variance of p hat will in fact be p hat into 1 minus p hat divided by the number of replications, just from the variance of a proportion. And if we take as an example experiment 7, so we take this one and evaluate what this variance of p hat is, remembering that the number of replications n is 100. This turns out to be, well, if we now take the standard error, 0.03. So that when we look at that empirically determined rejection proportion, it could in fact be in the range 0.07 to 0.13. So that in fact, for this particular one, when we know the asymptotic value should be the size of 0.05, the range on the empirical power doesn't cover this asymptotic one. So that particular case is one where the empirical power is poorly determined or approximated by the empirical one. But if you repeat these calculations for all the different values of p hat, you'll find that almost all of the p hats do have quite a large sampling standard error. And if you take the estimated value p hat plus or minus 2 standard errors, then that's quite a wide range. And this is the point I made at the beginning with Monte Carlos, that if the Monte Carlo is going to have any value, then you must be determining these parameters of interest accurately. And in this particular case, what we're seeing is that we haven't been able to determine the p hats very accurately. And that's not surprising because we haven't used in the design any variance reducing transformation. And that partly comes about because, for example, we haven't been able to think of any control variate for this rejection proportion. If we were able to find any variance reducing method, then we would probably do much better. What else do we notice in these results? Well, certainly as the sample size, capital T, becomes large at 75, that's very large by econometric standards, then apart from this case where the empirical size was 10% rather than the 5%, the other two cases give us values which are very close to 5%. And all these results do give us, first of all, close agreement between the empirical power and the asymptotic power. And apart from this last case, the power is quite high for the test statistic. But in the last case, the power is very low. Now, can we work backwards and say, why is the power low in that particular case, even when the sample size is large? And the reason there is that the signal-noise ratio is in fact very low for that particular case. And the signal-noise ratio is given here, and that's not directly a variable which we're controlling. It follows from these controlled values. And for this final experiment, the signal-noise ratio is only 0.1. So the variance of the x variable that's coming into the model is very, very small relative to the variance of the random disturbance term, epsilon. In that situation, it's going to be very difficult to have a test with high power, and that's exactly what we're finding in these Monte Carlo results. And if you go through the rest of the table, and wherever you find that the signal-noise ratio is low, so the third experiment, and if you look at all the powers for the third experiment, again, they're very low. Reversing that argument, whenever the signal-noise ratio is high, as in the fourth case, where it's 53, the power should be very high. And if you go through that column, you find this close agreement between the asymptotic approximation and the empirical power, and the power is high. And there are two messages that come out of that Monte Carlo analysis of this static model. One is that in most cases, the asymptotic approximation to the power is a very good prediction of the empirical power in small samples. And the second one is that the power varies directly with the signal-noise ratio. Well, there has also been some work done on a dynamic model, so that's setting off with systematic dynamics and then a dynamic error process. I haven't time to discuss that, and I'll leave you to read that if you're interested when it's published. Well, as I indicated at the beginning of the course, model selection in econometrics is really what econometrics is all about, and it's what econometricians are doing all the time. It's a very complex problem, and unfortunately, in practice, some completely arbitrary and ad hoc solutions to this complex problem have been used. What I've attempted to do in the lecture course is to give a survey of some of the more systematic and rigorous approaches to model selection. And for static models, there are some uniformly most powerful testing procedures. As soon as we come to determining the appropriate choice of models in dynamic contexts, then the problem is very much more complicated, and it's not even possible to derive uniformly most powerful testing statistics asymptotically. And that was the reason why we had to embark on the Monte Carlo study of the particular procedure that has been proposed. And the final point to remember is that in the end, we shouldn't expect purely mechanical procedures to be valid for determining the appropriate model. And the distinguishing feature of an econometrician, as opposed to a data analyst, is the fact that he uses economic theory. And I hope that message has come through in the lectures, that in the end, it's going to be economic theory as much as statistical analysis which determines the appropriate model.